Chapter 14, Acids and Bases. There are a number of different acid and base definitions that we're going to use, but we are going to start out with an Arrhenius acid and base. And this is the same Arrhenius that we had when we discussed activation energy back in our kinetics chapter. And we're going to look at his definition of acids and bases first. So the simplest definition of an acid is that it's a substance that contains an H plus and it donates it or loses the H plus in an aqueous solution. So, for example, if you had HCl and you put it in water, it could take and produce H plus and chloride here. This is aqueous, and this would be a nice definition of an acid. So something that produces H plus in water. H plus, by the way, is also a proton. We're going to use that definition later. A base is a substance that contains OH minus and produces it in water. So something like sodium hydroxide. If we take and we put sodium hydroxide in water, it's going to make N plus and OH minus, and something that produces hydroxide in water is going to be a base. There are a lot of common acids that we have. We have things like carbonic acid, which is what we have in our sodas. We have acetic acid, which we have in vinegar. Phosphoric acid is the acid that we have in sodas. It's also used in fertilizers and a number of other things. And we've got some nice strong acids that are, among other things, explosive, which is kind of cool. Our strong bases are used in a lot of things, especially soap. But we see our sodium hydroxide and potassium hydroxide. These are referred to as lye and caustic potash. Baking soda we use for cooking as well as an antacid, and there are also a number of other bases. These are the common ones. Okay, structure of acids. We have a couple of kinds of acids. We have binary and we have oxy. Binary acids would be a hydrogen with one other element, so two elements in total, and it would be things like HCl or H2S would be nice binary acids, and this is the hydrogen that is lost or donated in water. Oxyacids are the most common kind. They're inorganic oxyacids, and it means here that there's oxygens involved, and they are things like HNO3 and H2SO4. And note in these guys, the hydrogen is actually attached to an oxygen. So in nitric acid, you would have the oxygens and the hydrogen would be attached to one of these oxygens, and this hydrogen would come off as an H plus when it is put in water. In sulfuric acid, there's two hydrogens, each of which are attached to an oxygen. There are also a number of organic acids where it would be some organic group, which we refer to an R, and it's going to be attached to a COOH, that's a carboxylic acid, or an R attached to an OH, and that is an alcohol. Example of this would be acetic acid, CH3COOH, and this is the acidic hydrogen, again, the one attached to an oxygen. An alcohol could be C6H5OH, which would be phenol, and again, this hydrogen right here at the end would be the hydrogen that would come off when this is put in water, making these nice Arrhenius acids. Arrhenius bases. Now, not all the bases that we're going to discuss here are going to be Arrhenius, but we'll look at the structure of them. Most of them are inorganic, and they contain hydroxide ions. And these would be in general groups 1 and groups 2. So, for example, NaOH and KOH are going to be inorganic compounds that produce OH minus in water. Group 2 does it as well. So we have calcium, strontium, and barium hydroxide. When you put these guys in water, they're actually going to make 2 hydroxides. And this is going to be a nice base. But most organic bases, or most bases are organic, and they contain amine groups, and they contain a nitrogen with a nice lone pair. Now, the prototype, while it's not organic for this, would be ammonia. And what happens is that an H plus can come and stick onto that lone pair on the nitrogen, and that is actually we're going to discover is what's going to make it a base. Other varieties of this could be something like CH3 with an N, and if you have this nice nitrogen with a lone pair on it, it is going to be a classic base. So what happens when you put these guys in water? If we look at our Arrhenius bases dissociate in water to produce hydroxide. So they're going to contain and produce hydroxide in water, and the classic would be sodium hydroxide. Acids ionize in water. These guys break apart back old in our solubility rules. Acids, on the other hand, are not actually ionic. They're made up of they're molecular acids, so they can't just dissociate. Only ionic compounds can dissociate, so they have to be pulled apart or ionized by the water. And in the case of HCl, it is going to ionize into H plus Cl minus. In a lot of acids, the H's are written in front. In the organic acids, they are not. They are written as a COOH, but I think our textbook does it this way. Either way, these are both acids. It's the same compound. This is acetic acid, and they're going to ionize in water to make an H plus and the leftover anion. So we have a problem with our H plus. H plus is a proton. We know a proton is a subatomic particle, and we know that these do not exist in nature. So what happens with our protons is that our protons are going to stick to water and make H3O plus. So in fact, no H pluses exist in water. They stick to water and they make hydronium. So all H plus in water is in fact or exists as H3O plus sticking to the water, and it will make hydronium. Now, we have a few problems with the Arrhenius theory. One of them is that Arrhenius defined a base as something that contained and produced OH minus in water. Well, things like ammonia do not contain OH minus, even though they do produce it in water. And the other problem is that some things, also like sodium carbonate or sodium oxide, when they go into water, they do not contain OH minus, even though they make it when they are in water. So we're going to have issues with our Arrhenius theory. So we're going to have to come up with a new one.